Well, good afternoon, everybody. Thanks for dialing in to our January Flight Mechanics TDT monthly meeting. Starting off the agenda today, we're going to have a technical topic. Scott Karn is from Glenn Research Center, and he's going to be talking about the overview of the NASA Spacecraft TRaDe Modeling System, a rapid mission analysis tool. Before I begin with his biography, I need to read this notice. So the presentation is being recorded and made available to the public. So if you do not wish to be seen or heard, please do not activate your camera or microphone. So Scott just spoke about this topic last week at the AAS AIAA conference, and I asked him to bring this to our team meeting. He is an aerospace engineer with HX5 LLC in the Mission Architecture and Analysis branch at Glenn Research Center. As a member of the Power and Propulsion Element Gateway Mission Design Team, he focuses on the design, analysis, and optimization of low-thrust, multi-body trajectories for Gateway. Scott has a bachelor's and a master's degree in aerospace engineering from Case Western Reserve University in Cleveland, Ohio. So welcome, Scott, and we'll let you get going with your presentation. And I would just ask if you guys have a question on the TDT, raise your hand, and I will try to flag Scott if he doesn't see you to ask questions, but please ask questions when you're ready. All right, go ahead, Scott. Take it away. Thanks.
Thanks. Just want to confirm that my slides are displaying correctly and that's all good to go.
Yes, they look good.
Okay, perfect. Yeah, so like Heather said, I gave this talk last week at the Space Flight Mechanics Conference. So this is a pretty high-level overview of a mission analysis tool that we've developed at NASA Glenn. Because it is clear to export and everything, it's pretty high level. It focuses on methodology. There's not a whole lot of like hard numbers or data in here, but I'll do my best to provide context as we go. So NSTRDMS is a rapid analysis tool that was developed at Glenn primarily to fill a capability gap in terms of the tools that we have available to our team on the Power and Propulsion Element Mission Design team. So with PPE, we're focusing primarily on a low thrust trajectory, and the nature of those is that they're relatively resource intensive, both in terms of computing power and in terms of man hours, just analyst time. And running an extensive set of trades on low thrust trajectories can be really difficult without large computing resources. But with the demands of the project changing, relatively rapidly, we often have quick turn analyses that need to get out the door pretty fast. And so using our high fidelity tools to run trades on these low thrust trajectories can be kind of infeasible within the timeframes necessary. So over the last 2 years, we've developed NSTRDMS primarily to run trades on vehicle mass, power, and propulsion system performance as it relates to PPE. We've also, over time, added in the capability to take a look at launch vehicle performance and the effect of launch date, as well as a couple other items that I'll talk about. And the base methodology of NSTRDMS was designed to be modular. So it was designed to incorporate new additions and updates rapidly over time, just to meet the evolving demands of the program. So I'll give a really brief overview of the background motivations for this. I don't think I need to go too much into detail about what Gateway is, but Gateway is going to be a habitable outpost in cislunar space going up in the next few years. It's going to support human exploration in the cislunar environment and then surface operations on the moon as well. And the first two elements of Gateway to be delivered are going to be the power and propulsion element, PPE, and the habitation and logistics outpost, HALO. Those two are going to be co-manifested as the CMV, and then they're going to launch and complete their transfer to the moon together as a single stack. The transit by which CMV will go from launch vehicle out to the moon, we just call the lunar transit trajectory, but it takes advantage of the solar electric propulsion system on board PPE to push this relatively large spacecraft all the way out. I'll go into a little bit of detail about how we've designed and constructed the trajectory. We have another paper that we've published last 2 years, I think, that I could supply to the team. If you guys have more questions on this transit, or just feel free to email me and then I can answer any questions you have. But we're delivered into a highly elliptical parking orbit by our launch vehicle, and you can kind of see where we start in this graphic on the right. Then we launch into a spiral phase where we have a long EP spiral, just trying to raise the energy of our orbit as quickly as possible. That's in red. In orange, which might be a little hard to tell the color differential on the graphic here, but in orange we transition from spiral to alignment phase, where we're essentially trying to align our trajectory with our insertion into our target NRHO. So in the spiral phase, we're mostly doing tangential thrusting, trying to raise our orbit quickly. In the alignment phase, we're starting to do more out-of-plane thrusting just to change our alignment. Then we go ballistic for a bit and coast out to the moon before we have a few targeted lunar flybys, and then finally our insertion into the NRHO. But so this is a large, long, complex, low-thrust trajectory. There's multiple phases. There's multiple different construction methodologies that go into building this trajectory. And so designing and optimizing it is relatively intensive in terms of computing power. We primarily use Copernicus on the PPE mission design team. And anybody that's worked with Copernicus before knows that designing a trajectory like this that has a lot of segments, a lot of variables going into it, it takes a long time to converge and optimize a single case. So if we were to then take a baseline trajectory and try to run a TRaDe analysis with it, we could very quickly find ourselves outpacing the computing resources that we have available. And running these large TRaDes, even with clusters or servers of machines, it can quickly become infeasible, both in terms of resources and in time. So to try to ease that burden, at least when it comes to TRaDe analyses, we've developed this methodology that's allowed us to have a far simpler analysis space when it comes to our lunar transit. So some work that was completed previously by the PPE mission design team, and I think Laura Burke is on this call, and she contributed quite a bit to this before I was part of the team. But previous work has shown that the delta V required to reach our NRHO maintains a strong correlation to the initial apogee altitude of our parking orbit. This is possible because from DRM to DRM, and as we move through different design cycles of PPE, the parking orbit perigee is held constant at 200 kilometers. That's an operational constraint, and also comes, I believe, from some heritage missions with our prime contractor. But because of this constant perigee altitude, as we change other aspects of the vehicle, the only degree of freedom in an inertial parking orbit is apogee altitude. And so we can parameterize the delta V required to reach the NRHO by the initial apogee altitude of this parking orbit. And that's this red curve here on the right. And you can see it's a relatively clean curve fit here. And this is a fit to Copernicus data. So behind these lines are a large number of runs in Copernicus that we've then fitted these curves to. But this is a relatively simple methodology. It's just delta V as a function of a single variable. But you can also apply this methodology to pretty much any orbital state of interest throughout our trajectory. So I talked a bit about how we switch from a spiral to an alignment phase in our transit. That happens at a vehicle semi-major axis of 130,000 kilometers. So we can just parameterize the delta V to reach that switching point by the same initial parking orbit apogee altitude. And it just yields a different curve that then can be loaded into our tool. So we've also applied this to things like raising our perigee above the altitude bands associated with the Van Allen belts, so getting out of the radiation belts. And we've also done the same thing for getting out of the atmosphere down low and escaping the drag effects and things like that. So we've taken the same methodology and applied it to multiple different orbital states throughout the trajectory, in addition to the total delta V. So with this relatively simple delta V parameterization, we can build out a far more complex model of the entire PPE vehicle and the mission. So down in the subsystem performance level, so 4 blocks down here, we have models of our solar arrays. We have models of all of our individual thrusters and PPE. Then we can integrate a model of the vehicle itself, or we can get a spacecraft mass. We can couple that mass with launch vehicle performance, which will then feed our apogee altitude parameterization. And all of that essentially just gets shoved into a single rocket equation calculation at the very top. And that is really what forms NSTRDMS. So we have all these individual elements that have their own individual models. And by modeling all of those systems, the interdependencies between them, we can build up a integrated analysis environment around PPE. And that's really the basis of NSTRDMS. It's a system of systems or a model of models. So getting into what these subsystem models actually look like, the first and kind of the most critical for PPE is our solar electric propulsion system. We have a relatively large solar electric propulsion system on PPE, 50 kilowatt class. That's made of 7 individual thruster strings of 2 types. We have 3 13 kilowatt thrusters and 4 6 kilowatt thrusters. We also have 2 different operating modes on our 6 kilowatt thrusters, a high thrust and a high ISP setting where we can kind of shift the efficiency versus the thrust output of those strings. But all of that is to say that we have a complicated IPS system where we have multiple different thruster strings, multiple different operating points. All of these strings are throttleable within a specific power input band. So we have a large number of possible permutations of our propulsion system. But by taking throttle curves and models directly from our EP team and feeding them into NSTRDMS, we can create an accurate model of our EP system. And this will actually get fed into a higher order IPS management algorithm, which I'll talk about in a few slides. To feed all of these EP thrusters, we have our solar arrays on PPE. Again, we take a power output model directly from our electric power systems team. We feed that into NSTRDMS. We actually model power in the same way that Copernicus models power, which is just with this one relatively simple equation at the top here, where power to the thruster is a function of the power output of the arrays, and then you subtract off the power required to run all of the non-EP functions of the vehicle. And then there's a correction factor that gets tacked on to the power output of the arrays, and that takes into account range to sun as a function of 1 over r squared. And then there's also a time degradation effect that takes into account things like orbital debris impacts and damage from ionizing radiation. So we get a model from our EPS team, and then we actually develop these coefficients that you see here, the G1 through 6 and T1 through 4, so that we can have a model that is consistent between our high fidelity model in Copernicus and our low fidelity model in NSTRDMS that also matches the inputs that's given to us by the EPS team. And then coupling our vehicle model with our trajectory model is our launch vehicle. So again, we've parameterized the total delta V for our mission as a function of the initial parking orbit apogee altitude. That initial apogee altitude is a function of spacecraft mass and launch vehicle performance. Obviously, a higher performing rocket is going to be able to deliver a specific mass to a higher apogee altitude. So SpaceX, together with the Launch Services Program at Kennedy, provide us with a model of expected launch vehicle performance, which for CMV has been contracted as Falcon Heavy. So we get a series of data points for expected mass to altitude performance, and then we just fit a curve to that, and it gets its blessing from SpaceX and LSP. Functionally, it ends up looking kind of similar to this curve on the right. This is actually from SLS. But so then we can just go ahead and pick off what is our expected apogee for a given spacecraft mass, feed that into our parameterization, and get a delta V back out. I'll talk a little bit about what the limitations of this tool is later, but one of the critical ones is that we ignore a lot of things in NSTRDMS to enable this rapid low fidelity analysis. One of which is tied to our apogee or our parking orbit. So things like AOP and RAN and the alignment of our initial parking orbit are to have an effect on mission feasibility, but we ignore all that and we just take a look at what our altitude is so that we can get this delta V parameterization. But I'll talk a little bit more about limitations at the end of the presentation. So I mentioned that we have this IPS management algorithm. Getting into it a little more, we have this complicated EP system where we have multiple thruster strings and multiple operating points. At any given time in the trajectory, we may want to change our IPS configuration for various reasons. Our nominal baseline is that we use that high thrust set point that I was talking about for the spiral phase. And then once we switch into the alignment phase, we switch over to a more efficient high ISP configuration. So we switch operating points. That comes with different throttle settings for all of our thrusters. If we were to experience a string out thruster failure along the way, we would have to completely change our IPS configuration again. And so the management of the IPS system can get very complicated very quickly. And in high fidelity tools, and specifically in Copernicus, it's very difficult to model individual thruster strings and their behavior. Copernicus actually just models one monolithic engine as opposed to individual thrusters. So there's a lot of onus on the mission designer to do all the back-end polishing and post-processing of the data to back out what individual thruster strings are doing throughout the mission. But in NSTRDMS, we've integrated a native algorithm to do all of that for us. So we track all 7 individual thruster strings throughout the entire mission, whether they're being used or they're not being used, or whether they're in a specific set point or a different one. And we couple that with a user-defined thruster priority. So our baseline in PPE is that we rely mostly on our 13 kilowatt strings to do the lion's share of the work for us. So we bias the throttle input to our 13 kilowatt strings, and we throttle back the 6 kilowatts in order to maintain that power to the bigger thrusters. We take that user-defined thruster priority, where we're trying to maximize power to our 13 kilowatt strings, and we use that to dynamically throttle all of the thrusters throughout the mission profile. So as we march through different time steps in the trajectory, NSTRDMS is actually calculating the power off of the arrays, then distributing that power accordingly to thruster strings in accordance with our thruster priority, and then tracking the performance of each individual string so that at the end, we can pull off throughputs, operating hours, delta V expended for each individual string. So this is actually a really critical step. This is what makes NSTRDMS really valuable within our analysis tools. And it's greatly simplified the amount of work that's needed by the mission designer, because I don't have to sit here and essentially babysit the IPS system or create multiple different engine configurations before I can run an analysis. I can just input the number of thrusters that I have available, which is nominally 7, and a thruster priority, and NSTRDMS will do all the management work for me. So how do we actually solve for a trajectory? The first thing we do is we create this virtual CMV that integrates all of these different models of all of our different subsystems. And then we march that model forward in time, day by day, essentially, to solve for our mission. So for any given day, we calculate the power that is being generated by the solar arrays, and then we subtract off the vehicle loads. So from that amount of power that's available to SEP, our thruster priority algorithm throttles all of our thrusters accordingly to use up all of that power available, but it also checks for things like whether or not thrusters have hit lifetime limits or if a thruster has failed. So from an available power, we calculate what is our desired configuration for a given day, and we distribute power. Then it's a relatively easy calculation to determine time times mass flow rate of your thruster configuration to get a propellant expended for a given time step. And then that just gets fed into a rocket equation calculation to get the amount of delta V that you've output in a given day. And so day by day, we just run this loop over and over and over again, tracking the amount of delta V that we've expended until finally we hit that total that was calculated with our apogee altitude parameterization. So when we hit that number, we've reached the NRHO and the trajectory is complete, and NSTRDMS considers the mission fully complete and PPE and HALO delivered to the NRHO. So This tool is used quite a bit within the CMV program to support a number of different analyses tasks. But so the efficacy of the tool relies on the validation of the results. So we are regularly and continuously validating NSTRDMS results back against our high fidelity Copernicus outputs. So we run in design cycles where we output different design reference missions over time. The original development of NSTRDMS took place back during DRM2. You can see that we did pretty good against DRM2 in terms of being able to replicate the trajectory. We had errors in under 1.5% in terms of our major figures of merit, which are time of flight, propellant consumption, total impulse, and mass delivery. Between DRM2 and DRM3, we actually completely rewrote our methodology and increased the fidelity of the tool quite a bit. And in doing so, we were able to minimize a lot of those errors. So now we're down under 1%. And we've continued to expand the capabilities and the complexity of the tool from DRM3 to DRM4, and now we're developing DRM5. But we've maintained reliability relative to our high fidelity results. So the tool has continued to be a valuable way with which we can run rapid TRaDe analyses and be confident that those results are representative of high fidelity solutions. So what do results actually look like for NSTRDMS? Rarely do we do one-off, just single set point results in NSTRDMS. It's not really what the tool is optimized for. We really use this tool to run large TRaDe spaces and large spreads of potential inputs. So one of the first things that we started doing in NSTRDMS that became really valuable to project management are these flight envelopes for CMV. So we run through a matrix of apogee altitude and vehicle mass combinations, and we run trajectories for each one of those set points, and we form this kind of contour plot at the end. And then over top of our solutions, we can layer a couple different figures of merit. So the green contour shaded region in the upper right, that's all of the initial apogee altitude and mass combinations that are beyond the capabilities of our launch vehicle. So we just cannot attain those launch conditions. Everything in purple in the upper left, that exceeds the propellant capacity of our vehicle. So we just don't have the ISP to launch with that mass. And then everything in salmon is time of flights that are over 365 days, which is, 1 year is just a nice kind of reference point to compare different trajectories to. So everything below those red lines represents feasible trajectories in terms of launch vehicle capability and propellant capacity, so really high-level mission constraints. But these plots are really useful to management. It helps you compare different trajectories, different DRMs, just by seeing, what direction are they headed on this plot. But critically, there's 1,250 solutions in this plot, and for some of these flight envelopes, we do more. Rarely do we do less. This is 1,250 is kind of the minimum. But NSTRDMS executed all of those results in 21 seconds, which is just completely infeasible. If you were to do this in Copernicus, it would take you multiple days of just computation time to develop 1,250 trajectories. And it would likely be a multi-week effort to sit there and actually run all of those. So being able to do it in under a minute is a significant increase. But so that kind of shows the capability of NSTRDMS to assess very large TRaDe spaces very quickly. Another thing that NSTRDMS has been used quite a bit for recently is assessing individual thruster throughout the entire mission. It's very easy for us to designate any one of the 7 to fail. And we can trigger those by mission elapsed time. We can trigger those by thruster throughput or impulse or delta V through that thruster. So we have multiple different ways with which to essentially trigger a failure scenario. But then we can also assess a wide variety of recovery scenarios in terms of what IPS configuration and what permutation of our thrusters do we move to satisfy the rest of the mission. And so we can go through and we can assess all these different failure scenarios across a wide range of vehicle masses and across a wide range of mission elapsed time at which that failure occurs. And that's this contour plot that you see here. So, and then over top of this, I've layered propellant margin in terms of percentage. So In the upper left, you have a fairly light CMV with a very late failure. And so the result being that we have a really good propellant margin at the end of that trajectory. And then down to the bottom right, we have a very heavy CMV with essentially a day one failure of a 13 kilowatt string thruster, which is one of our priority thrusters. And so those cases, at least in the strategy that was used for this analysis, exceed our available propellant margin. So those are infeasible trajectories. We just don't have the fuel to complete that mission. But so to quickly wrap up, NSTRDMS, it's a rapid analysis tool. It's a low fidelity TRaDe analysis tool that is designed to run TRaDe cases that are just infeasible in things like Copernicus. We've expanded the tool quite a bit over time. We are regularly validating our results back against our high fidelity tools. But part of that is that NSTRDMS carries a lot of limitations as a low fidelity tool. It's a mission analysis tool. It is not a trajectory design tool. So NSTRDMS cannot natively develop trajectories on its own. It can only perform analysis on trajectories that already exist. So at minimum, we need some sort of delta V parameterization with which to feed NSTRDMS so that it can go off and do all of its analysis. There's also a lot of effects that we ignore in NSTRDMS that do come into play in the higher fidelity solutions. So I talked a little bit about the initial orientation of our parking orbit. There's also things like atmospheric drag, solar radiation pressure, and there's also varying amounts of plane changes that are required in our alignment phase that may not be captured once you start ignoring like the 3D environment that you would get in Copernicus. So NSTRDMS is not meant to be a high fidelity solution. It's not meant to give you a high fidelity result. It's supposed to get you in the ballpark of what you would expect if you were to run that specific case with Copernicus. And a lot of the times NSTRDMS is used to identify cases that we want to go look at more in Copernicus, or it's used to identify initial guesses so that developing those trajectories is a little easier in the high fidelity tools. And then I think one of the primary reasons why Heather wanted me to present here is, what are ways that this methodology could be expanded in the future beyond PPE? This is a really PPE specific tool at the moment. But part of the nice thing about PPE is that we have this spiral which exhibits relatively reliable and predictable behavior as we start changing different elements of the mission. And so NSTRDMS is a purely analytical solution, which in terms of low thrust trajectories and multi-body dynamics, purely analytical solutions are fairly rare. So in terms of expansion beyond CMV, NSTRDMS really has a future as a way of analyzing spirals as a whole, which is something that you can look at analytically. But there's a lot of use cases where NSTRDMS just really isn't the solution because of the level of complexity required with assessing those trajectories. But we've designed this to be modular. We've done this to be kind of plug and play, so you can replace power system models very quickly. You can replace propulsion system models very quickly. If you do have something like a spiral that can be parameterized by some independent variable, you can very quickly put in a new delta V estimate or a new delta V curve and run entirely new tool or entirely new trajectories. This has been used once in one of those cases at the Compass Lab at NASA Glenn. We have a rapid mission analysis group here that runs different studies for different customers. I used NSTRDMS to support an analysis of a different cislunar mission where it was a spiral into LLO from a translunar injection. But so for different mission sets and different propulsion systems and different vehicle masses, I can run that spiral through NSTRDMS very quickly. And so this was very useful for that analysis. And it only took about a day of work to get all of the inputs set up to run that mission instead of PPE. So there is a future. I think that the methodology of this tool kind of lends itself to analytical solutions, which ultimately will limit it in the end. But that is all that I have to talk about today. So if there's any questions, I'm happy to take them. And if not, I thank you for your time.
Thank you, Scott. That was wonderful. Do we have any questions from the TDT online members?
Hey Scott, Bill Benson here. So this is a topic near and dear to my heart because I'm working the launch vehicle piece of the CMV mission. So it sounds like basically, how is Nostradamus generating all this data? If it's not propagating trajectories itself, it sounds like you're basically taking reference trajectories from a high fidelity tool like Copernicus. And it almost sounds like you're basically interpolating between the various points, but it's more sophisticated than that, I would think.
That's a pretty good descriptor, yeah. So and I'll jump way back to this curve. Okay, so this red curve is our delta V parameterization, but essentially this is exactly what you're saying, where this curve is actually made up of dozens of different points that are Copernicus solutions, which you can think of as reference trajectories for different apogee altitudes propagating all the way out to an insertion into the NRHO. So yeah, we essentially are interpolating between all those solutions so that we don't have to run a full end-to-end trajectory in Copernicus. We can just use this interpolation as our starting point. And then the understanding or the assumption here is that interpolation holds steady as we change all sorts of different things about the vehicle. So our propulsion system performance, our mass. And that has been the case. We have seen that reliability behavior is steady. And a lot of that is based on this previous work that the MD team has published. And there's a reference in here, and I can send that paper out if you're interested. But yeah, you essentially nailed it on the head. This is essentially an interpolation tool that then is lumping a bunch of other complex stuff on top of it.
Okay. Yeah, very, very informative. So when you're failing like these different strings on the xenon propellant system, you're just basically using the rocket equation to figure out, okay, what the implications for that would be as far as propellant usage and what have you. Okay.
Yeah, that's correct.
Got it. Okay, thank you.
Scott, I had a question. On your last slide, you talked about, how this tool can be adapted for different propulsion systems. What would it take if you wanted to evaluate like a hybrid scenario where you had a combination of a low thrust and a traditional chemical thrust system?
So that would be relatively easy within the framework that we've built. So you just put in essentially throttle curves for your chemical system and whatever relatively chemical system and your EP system. That would require changing the IPS management algorithm that I've put in. So you'd have to change the way the thrusters are being used by the tool. But that's just a matter of going in and changing, one specific function within, this is written in Python. So within the entire script, it's one specific function manages that. So it wouldn't be horribly difficult. The really critical thing there is that you have to make a lot of assumptions in order to get this framework to work. So for something like a hybrid mission where the amount of EP delta V that you need to expend is very sensitive to the size of your chemical stage and also the duration of your mission and what your destination is. So you might have to do a lot of work to get this kind of simple methodology to work for a complex mission like that. But without actually going through and doing the work, I wouldn't be able to tell you how hard that would be.
And so for like a solar sail mission, what's your thought about using it for something like that?
That would be difficult because we explicitly are ignoring SRP. This is really a rocket equation calculation going on, and Bill was able to catch that. That's really what this is. It's running a rocket equation calculation just a lot of times, and it's not modeling the geometry of the trajectory at all. So something like a solar sail, I think, is kind of beyond the capabilities of Nostradamus.
You also mentioned that you had done some comparisons, to just, I guess, to anchor this tool, your outputs. Have you documented that, or was that is some of the content of another paper if you were comparing it to other high fidelity tools?
We have not compared these results to other high fidelity tools, just because we've validated this within the scope of PPE, and we are pretty much exclusively using Copernicus at this point to do our trajectory development for PPE. So every design cycle, every DRM that comes out, there's one specific case that gets pulled and used as the design reference mission, but there's a spread and a scan of solutions behind that one specific point. So we might run a scan for different launch dates, different initial orientations of our parking orbit, things like that. And so each one of these is a one-to-one comparison of a single Nostradamus solution against that single Copernicus DRM. But we also do validation against that whole scan of solutions, just to see, what is the spread that we are expecting and what is kind of the error bars on these analyses. I don't know that we've published those results publicly. It's kind of something that we hold on to internally. And truthfully, no one within the project has asked to see it, which is probably the reason why we've never published it. But so yes, we have done more validation than what's shown here, but I don't think it's included in the paper.
Okay, thank you.
Is that sort of an automated? Sorry, is that sort of an automated process, or is that kind of a, the developer takes some time every once in a while to take a look at those?
In terms of the actual, hitting go on the analysis and seeing what pops out, that's pretty automated because we can load in, like a CSV file with all of the figures of merit that we're comparing against, and see what the deltas are. But so every DRM, we try to revalidate the tool. And so DRM 5 is going to be coming out relatively soon, and so I'll go in and do a whole nother validation. But so yeah, it's automated, but I have to actually take the step to go and hit go. I don't know if that answered your question, Rob.
I was kind of curious, like, a lot of times with trajectory analysis, and this is analytics, so it's not quite the same thing, but there's a lot of different places where things can be different, and so it seems like it might be difficult to say. It's like, well, we matched pretty much everything, but now this one number is off a little bit, and you have to. So I'm just kind of curious how you make calls like that and decide, like, what's your metric for good enough?
Yeah. So the goal is that the error that we see from the Nostradamus results relative to a Copernicus solution, we want that error to stay within the spread that we see just in developing a single DRM. So to give everybody an idea, there's a low fidelity trajectory, and it's sensitive to a whole lot of different parameters, which Rob just touched on. But so for a single design reference mission, we might generate 1,000 or more trajectories, and there might be a plus or minus 7-day delta in time of flight across all of those different possibilities. And there might be a plus or minus 2 to 3% propellant usage across all of those. So as long as the errors that we're seeing out of Nostradamus stay within that kind of cloud of Copernicus solutions, we call that good enough and that we're happy. So we try to make sure that the sensitivity of the tool is inside of the sensitivity of the solution space in Copernicus.
Thanks.
Well, and if there's no other questions, then I'll stop sharing.
Thank you, Scott. I would encourage any others that might have questions to reach out to him. He's in the global, and we'll certainly give you his contact information if you're having troubles there. But thank you again for presenting today. And this should be eventually uploaded on the Academy. So if you've missed it, you can circle back and watch it there. So thank you again, Scott, for bringing this to our TDT.
Yeah, thanks for having me. Thanks for your attention. Yeah, and feel free to reach out if you guys have any other questions in the future, whether it's Nostradamus or PPE related.
Great. Thank you.
Thanks.